For years, a major roadblock in quantum computing has been how to build robust, fault-tolerant systems without an explosion of physical qubits. Today, we're looking at breakthroughs that could completely change that trajectory. Let's start with this paper about quantum LDPC codes.
Indeed, this work is tackling a fundamental hurdle in quantum low-density parity check codes. They're trying to achieve the kind of efficiency and performance classical LDPC codes offer, but the quantum world adds a layer of complexity, orthogonality constraints.
Orthogonality constraints. That sounds like a fancy term for things getting in the way. What specifically do these constraints do to quantum LDPC codes that make them so difficult to design?
In essence, these constraints, like the HX-HZT equals 0 condition, prevent quantum LDPC codes from easily achieving a large girth, which is critical for good decoding performance and a strong minimum distance. It fundamentally limits their error-correcting capability if not handled carefully.
So, how did this team manage to navigate around such a fundamental design obstacle? What was their core insight to improve these codes?
They designed a clever construction using permutation matrices that controls how these matrices commute. Crucially, they restricted the orthogonality requirements only to the active part of the code, not the entire structure. This avoids unintended limits on code performance. As a concrete demonstration, they constructed what they call a girth 8, 312 regular, 9216, 4612, smaller than 48, quantum LDPC code. This is a significant parameter set for anyone working on these systems.
That's a lot of numbers. For our builders out there, what does girth 8 mean for the actual performance of the code in a quantum computer?
Girth 8 indicates a highly connected but sparse graph structure, which translates directly to improved decoding. The paper shows it achieves a frame error rate as low as 10 to the minus 8 on the depolarizing channel with error probability 4%, which is an excellent result in terms of error suppression.
A frame error rate of 10 to the minus 8 means we're seeing errors incredibly rarely, even with a relatively high underlying physical error rate. This level of reliability is exactly what we need for practical quantum applications.
Beyond just building codes, they explicitly address the issue of low-weight logical operators emerging from row deletion. This is a subtle but critical problem. If deleting rows to adjust code rate inadvertently creates these operators, the code's error-correcting capability is severely degraded. It's a bit like a hidden backdoor for errors.
So, they're not just making a good code, they're making sure it stays good when you try to simplify it. That's a deep understanding of how these systems fail in practice, not just in theory. It's a vital insight for robust code design. This paper shows the potential for highly efficient QLDPC codes, but even with great codes, we need fast and accurate ways to decode them. That brings us to our next source, focusing on hardware emulation for error correction.
Decoding is where the rubber meets the road. These codes generate complex error patterns, and interpreting them quickly in real time is paramount for practical fault tolerance.
Okay, so we have promising quantum LDPC codes. Now, how do we actually decode the errors these codes detect? And how do we do it fast enough for real-time operation? This paper zeroes in on that challenge, stating that QEC decoder performance is increasingly critical for scalability.
Precisely. The performance of these decoders directly impacts the number of qubits required and the overall system throughput. Moving from software simulations to actual hardware for decoding is a monumental step for practical quantum computing.
Instead of just simulating decoders in software, this team built a hardware emulator to evaluate QEC decoders using real hardware. How much faster is this approach compared to the traditional software-only methods?
The difference is striking. A single FPGA running at 150 megahertz on their emulator can explore 10 to the 13 different error patterns in just 20 days. That's an incredible speedup for validating decoder performance.
Wait, an optimized C++ software on an Intel Core i9 would take over a year to do the same work? That's not just a speed up, that's a paradigm shift for anyone developing decoders. You can iterate and test so much faster.
Exactly. This accelerates the design cycle for QEC decoders dramatically. Builders can quickly test hypotheses and optimize their algorithms against a vast landscape of error scenarios, something simply infeasible with purely software-based approaches. What's particularly innovative is their diversity-based decoder method. They combine multiple belief propagation decoders, each with slightly different quantization levels. It's an ensemble approach, much like in classical machine learning.
So instead of relying on one perfect decoder, they're using several slightly different ones, and their combined wisdom is better? That sounds like a robust strategy, especially when individual decoders might be imperfect.
The results show that this approach achieves a similar logical error rate as the well-known approach BP with ordered statistics, BP plus OSD decoding, with average speed improvements ranging from 30% to 80%. That's a significant gain for real-time systems.
Maintaining accuracy while gaining up to 80% speed is huge. It reduces latency and allows for faster feedback loops in the quantum computer's control system, moving us closer to truly fault-tolerant operations.
Another crucial aspect of this emulator is its ability to store uncorrectable error patterns, allowing for offline analysis and the design of new decoders. This is analogous to how classical hardware designers use sophisticated emulators to find corner case bugs before silicon fabrication.
That's brilliant. It's like a forensics lab for quantum errors. Identifying those specific failure modes gives engineers precise targets for improvement, which is a much more efficient development process than broad, generalized optimizations. So we have better codes and faster decoders. The next piece of the puzzle is how to make those physical qubits themselves more resilient, bridging the gap between error correction and error mitigation.
Indeed. Combining these strategies is where the true efficiency gains lie, reducing the overhead required to build functional logical qubits.
We've talked about error correction, but there's another powerful technique, error mitigation. This paper explores a hybrid approach, specifically quantum error correction on error-mitigated physical qubits. It sounds like they're making the underlying qubits better before QEC even starts.
That's exactly right. QEC protects information by encoding it across many qubits, while quantum error mitigation, QEM, reduces bias in measurements by running multiple noisy circuits. This paper marries the two at a very fundamental level.
In the near term, with limited qubit budgets, relying on either QEC or QEM alone isn't enough for many complex tasks. This paper argues that a hybrid strategy is essential. What's the main advantage of combining them this way?
The key advantage is resource efficiency. By mitigating errors at the physical layer before QEC processes, you effectively clean up the environment for QEC, allowing it to perform better with fewer physical qubits, thus lowering the overhead.
Past attempts often applied QEM at the logical level, which sounds computationally heavier. This research asks if we can apply QEM directly on the physical qubits and then QEC on top of the error-mitigated physical layer. What's the impact of this physical layer approach for builders?
The critical insight is that it simplifies the QEC decoder. By leveraging the linearity of QEC, they demonstrate that standard linear QEM methods like zero-noise extrapolation can be integrated at the physical layer without requiring modifications to the QEC decoder itself. This means less engineering complexity.
They mentioned that applying this framework, for example with probabilistic error cancellation, analytically proves and numerically verifies increasing the effective code distance by 2. This is a substantial improvement, isn't it?
An increase of 2 in effective code distance is very significant. Code distance determines how many physical errors can be corrected. A distance 3 code can fix 1 error, a distance 5 code can fix 2. So making a distance 3 code perform like a distance 5 effectively doubles its error resilience. Their simulations show impressive resource savings. A distance 3 code with physical level PEC achieves logical error rates lower than or similar to a distance 5 unmitigated code while using 40% and 64% fewer qubits. That's a huge reduction.
Fewer qubits means less hardware, less cooling, less complex control systems. For current quantum hardware, where qubits are a precious resource, this 40% to 64% reduction is a game changer for reaching larger, more stable logical qubits.
This hybrid approach provides a resource-efficient strategy for enhancing logical performance. It's a pragmatic bridge from today's noisy intermediate-scale quantum devices to true fault tolerance, leveraging both QEC's robustness and QEM's efficiency. It's not one or the other, but both.
It reminds me of how classical systems use both hardware-level error detection like ECC memory and software-level redundancy. This isn't just about finding the best technique, but about intelligent layering of complementary solutions to achieve a stronger overall system. So we're making qubits more robust and decoding faster. The final frontier is to make logical operations themselves more efficient and parallelizable, something that's been a persistent challenge for many codes.
Indeed, scaling quantum computation requires not just good logical qubits, but the ability to perform many operations simultaneously. Our next source tackles this head-on with a new architecture for QLDPC codes.
All right, final stop, parallel logic in quantum LDPC codes. Even with all these advancements, if we can't perform many logical operations at once, our quantum computers will still be painfully slow. This paper seems to address that core bottleneck.
This is a critical piece of the puzzle for scalability. Fault-tolerant quantum computing is not just about error correction, but about efficiently compiling complex algorithms using logical operations that execute in parallel.
They point out that in many QLDPC codes, logical qubits do not necessarily correspond to distinct groups of physical qubits. How does that lack of clear separation hinder parallelism, especially compared to something like the surface code?
The problem is entanglement. When logical qubits heavily overlap at the physical level, performing an operation on one might inadvertently affect another. The surface code's patches offer inherent isolation, simplifying parallel operations, but QLDPC often loses that clarity. To solve this, they introduce clustered-cyclic codes, a new family of QLDPC codes. The key is that these codes are specifically designed to have a directly addressable logical basis, meaning logical qubits are structured in a way that allows for independent control.
So they engineered the code structure itself to minimize that physical overlap, making it easier to target and operate on individual logical qubits? That sounds like a fundamental architectural improvement for QLDPC.
Alongside these new codes, they developed a technique called parallel product surgery for quantum product codes. This method allows for many logical Pauli product measurements to be implemented simultaneously in a single round.
I'm imagining a complex surgical procedure, but for qubits. So this isn't just about the codes, but also the operations on those codes, enabling them to be performed much more efficiently?
Crucially, for their clustered-cyclic codes, up to k/2 disjoint polyproduct measurements can be scheduled in a single round. This matches the theoretical maximum parallelism achievable with surface codes for 2-qubit operations.
Achieving surface code level parallelism with the density benefits of QLDPC codes, that's a huge win. It means faster algorithm execution without compromising on the efficiency of the encoding itself.
They draw an interesting analogy. While surface code parallelism is like a multi-core CPU with separate processing units, their approach is more akin to a quantum GPU. It's a single encoding block with intrinsic logical parallelism.
That's a fantastic analogy. Instead of explicitly routing logical qubits to separate processing units, the parallelism is baked into the very structure of the code. This could lead to a very different and potentially more efficient hardware design.
These developments across codes, decoders, and architectural design are truly accelerating the path to fault-tolerant quantum computing. It's exciting to see such rapid progress.
The cumulative impact of these breakthroughs is profound. We are moving closer to building quantum computers that are not just powerful, but also practical and scalable. I'm Maya.
And I'm Arjun. See you tomorrow.